Well, hello and welcome YouTube to Mr. Robinson's Q&A Power Hour. Today is December 13th. I was actually supposed to do this on December 11th, but my nephew came into town and I got a little busy. And you know, when a nephew comes into town, he's 3 years old and adorable, you gotta attend to his whims first. Hopefully this video won't take too long. I didn't get to see the questions, but I saw how many, and there weren't too many of them, so hopefully it'll fly pretty well. I am blending both of these in with my Integrated Math 1 and Integrated Math 2. Looks like I'm doing Integrated Math 1 first. They only had 4 questions, and Integrated Math 2 I think only had 8 questions. So given the Power Hour structure, we'll see how things go. Remember, check the description section down below to find where you can find the answer to that one particular question that you asked. And if there are other resources that I point to, if I find that I can, then I will. So I'm just going to jump straight into it, guys. Let's see what we got. And yeah, let's see. All right, so Integrated Math 1, I have 4 questions here. No, I didn't see these questions yet. They'll be answered the order that they're received. So here we go. Hi, Mr. Robinson. I have a question. I kind of don't get math, and I kind of do. Okay. But I wanted to ask you if you can help me just a little to get it more. Thank you. Well, of course I can. Of course I can. Just, you know, whenever. The Q&A Power Hour video might have other questions to check the next 3 questions here. Maybe your question will be answered there. You know, for my class, they're going to be taking an exam on Thursday and or Friday, depending on the period that they're in. And I have a solution guide video for their practice test. So hopefully that'll help them. And I have a lot of, to the person who's asking this, I don't know who you are. I have a lot of office hours and tutoring available this upcoming week. Monday, December 14th, 3:30 to 5:30 p.m. Tuesday, 7 to 8 a.m. and 3 to 4 p.m. Wednesday, 12:15 to 2 p.m. and Tuesday, 7 to 8 a.m. and 3 to 4 p.m. All of those days are available. There are some lunches I can do and things by request, but also check any of the other videos or see if this video has any other answers to what you have. I don't know if you're asking these next ones. Here we go. The next question is, hi, I need to take the test. Please see that. Okay. So do not go to the Power Hour video for this question. You might have been lingering on this since I don't know how long ago. The last Q&A Power Hour video I did was back in November before Thanksgiving break, a week before Thanksgiving break. So we're talking almost about a month ago. And you might have sent this all in right after that, for all I know. You need to email me about this stuff. Hopefully you already, I know a lot of people who have made up tests, so hopefully you were one of those people. Do not put this in a Q&A Power Hour video, because I answer things here that are based on content only, not curriculum and not individual whims such as this. If you still haven't taken a test because you've been waiting on this, email me, please. Okay, thank you. All right, hopefully, okay, thank you. Is there a difference in process of elimination by division and multiplication? Okay, so, well, no, but it depends on if there's a problem given in that setup. So, okay, hang on. So let's say you had a problem like, let me make sure it works both ways. Let me say I had a problem like 4x minus 2y equals 16, and let's say I had negative 8x plus y equals 4. I think this should still work no matter what. Okay. Now you have some options on what you can do here as far as eliminating, and I can see 3 totally valid options to make this thing work. I could take the bottom equation and I could multiply it by 2, because that would eliminate y. I'm not going to write the whole thing, but that would eliminate y. Negative 2y plus 2y is 0. I could take the top equation and I could multiply it by 2, because that would eliminate x's. That would give me an 8x here, and negative 8x plus 8x is 0. Or I could take the top equation and divide it by 2. Now, if you notice that you can do that, that might help you a lot, because that would give me a negative y right here, and that would eliminate the y's. And I say I can divide by 2 because it brings me down to that, but also because all these numbers can divide by 2. The whole goal and the idea, if I could do this, I would look to do it, because it just leaves me with smaller numbers, and to me, smaller numbers are preferred. So is there a difference? No. You're manipulating an equation still. You just got to make sure you do both the left and right side when you do it. And you still, and just so you know, this is another equation that you can use when I solve for x, I don't know if this is going to work. It looks like it is so far. Negative 6x equals 12 and x equals negative 2. I can now substitute that negative 2 into any of the other equations that you've seen so far. I could plug the negative 2 into this one right here with the smaller numbers, or this one right here, or this one right here. Or if you ever had a time where I multiplied this bottom one by 2, I'd get negative 16x plus 2y equals 8. I could have substituted the x into there, or I could have substituted into the top one if I divided the top by 2, and I got 8x minus 4y equals 32. It's one of the reasons I wouldn't want to multiply by 2 if I don't have to, because I'm getting larger values right here to plug in for x when I could use smaller ones here, especially that small guy. No, it doesn't matter whether you multiply, there's no difference in process of elimination between the two if you multiply or divide. We mostly look to multiply. See, when you divide, you have to not only find the number that divides to get into, which isn't hard, but you have to now guarantee that that number can divide from all three of your values. And if you can, that's kind of a process. There's another one, I don't know if I can create the equation like it that's going to work out, but another version, I don't know why I erase this way when I want to rewrite the problems. Let's say this was a 3y, and let's say this was a 9x, just to kind of change things up. Now, this probably won't give me good solutions. I'm making this up right now. Let's say this was a 3y and this was a 9x. Now, this might be where you can ask a certain kind of, this is where a good question can be asked as far as, Mr. Robinson, what should I do? Because it doesn't take, no matter what, it doesn't take one step to multiply or divide by any integer to get to eliminate anything here. I can't multiply -2 by an integer to get a -3, etc. So you have some options here. You could, and this almost goes beyond your question, but take a look at what I'm going to do. I could multiply this by 9 and this by 4, and that would give me a 36x and a -36x, and that would cancel those. Or I could multiply top by 3 and bottom by 2, and that would give me a -6y on top and a +6y on bottom, and cancel. The third option is this. I could divide the top by 2, and I'm not quite there yet, but I can now turn this -y into a 3y by multiplying the top by 3. So now if I multiply it by 3, I've kept my numbers kind of small, and now underneath I would have a 6x minus 3y equals 24, and then those would cancel. So I still kept myself with kind of small, and look, those x's, oh no, those x's wouldn't work. I kind of kept my values with kind of smallish numbers by dividing first there and getting it done, because these could still divide by 2. Then I could use that -y and then multiply by 3. So that kind of worked out as well. I mean, is there a difference in these? No. All of these things that we multiply by and such, they all give us answers that work in our system. But, I recommend you seek division if you know what you're doing with it. I haven't really asked my students to do it much so far because we haven't explored it a lot. Not a lot of problems have been set up that way, and I feel like people get a little when they see it. But every so often I do throw in that strategy. I like seeing it and using it. In fact, in my solution guide video, I point to that in one of the problems, but I say because we haven't been practicing it, I wouldn't do it, so I kind of didn't. Okay, so I hope that answers that question there. Thank you for it. Yeah, there's no difference necessarily, but there's good strategy involved if you can get it done right. The last question here in IM1 is, when solving two linear equations, does it make a difference if you either add or subtract? 11.3. What's 11.3? Eliminate. That's the for start of elimination. So you're asking if, I don't like, okay, well, you know me about subtraction if you've heard me before. Okay, does it make a difference if you, does it make a difference? It only makes a difference if you subtract. Get it? Get it? Okay. It makes a sum if you add. So does it make a difference if you add or subtract? It doesn't. I don't recommend subtraction, and I hope you've heard why before. Let me give the example for those who don't even know what I'm talking about and those who can understand my answer to this. Does it make a difference? No. Is it better to do one or the other? It depends on who you are. Because once you just saw me do the multiplication, the manipulation of things by multiplying, I recommend that you kind of stick to equation manipulation. But here we go. Let's say you had a problem. I don't know if this will even work. Let's say you had a problem like 4x plus 3y equals 7. Let me try and make it work. And x plus 3y equals 17. Wait, no. Wait, if I want to subtract, no. Hold on. I'm sorry. I'm thinking about this. Equals 22. Okay, I think that'll work. All right. There are several ways you can solve this like the last one. I could multiply the bottom by -4 to eliminate the x's, but I don't recommend that because I think I can eliminate y's a little better here because of their nature of how do you say it, being the same term. So what I personally like is multiply everything by -1. Multiply by -1, rewrite it with all the signs changed. You could, in fact, I would have done the top. That way, well, I don't know. But anyway, right here, rewrite that. Now I subtract. I got 3x. Those cancel, and that equals -15. Whoops, -15, and then I get x equals -5 like that, right? Then I use that one to solve for y by plugging in -5 into an equation. Now the question was asked, so this to me was addition, and the point I want to make here is you might see this as subtraction, but it's really not. What I'm doing, I'm doing 4x minus x, but the combining of like terms is adding a 4x with a -x. 4x plus -x. Do that again. 4x plus -x is 4x minus x, which is 3x. And you're like, so it's subtraction. Yeah, but the original combination became addition in that if any of these numbers were positive, it would be a plus. So if I add a positive, it's plus. If I add a negative, it's minus. So the origin of this is I wanted to change the signs so that when I add them, whatever the signs are is what I'm going to do. When I add a negative, it becomes subtraction. So I treat it like subtraction. That makes a lot of things easier for me perceptually. By the way, I wouldn't be done with this problem. I'd have to solve for y. If you want me to solve it later, I can. But what you could also do with this problem that I don't recommend is you could subtract from the beginning, meaning everything here becomes subtraction. You do 4x minus x here, 3y minus 3y, and 7 minus 22. There are a lot of reasons I don't recommend it, and there are a lot of... They come from the same reason. It's because sometimes students forget that subtraction is occurring, or they don't do the subtraction on something with a negative. It's this weird thing where they sometimes just subtract wrong. They do the opposite of something. In some parts of the problem, they treat it like addition. Sometimes people don't, like, you don't write the subtraction symbol. Some people say, and I'm going to subtract, and the first thing they do is they cancel out the 3 y's. I understand, they subtracted. Okay, that's fine. You got to keep subtracting, though. You know what some people don't do is they don't subtract these two. They say, okay, I'll cancel these out, and 4x plus x is 5x. Because you don't see a subtraction symbol anywhere. There's no operation that's telling you to subtract. You see these as cancellation because you wanted to subtract, and the rest you just start to say, I'm going to combine things. And you add this, and then you add this, and then all goes wrong. Or, you know what, you do write the subtraction, you do cancel that, you do subtract this one, and somewhere along the way, this one does not get subtracted. It's too far away from the minus for you to remember. And I'm not saying it literally, as I'm saying this is what will happen. It goes a little too far away. People forget the concept along the way, especially when they eliminate here, and they're like, where was I again? And then they just end up adding here. And it becomes one of those hassles. Now, there is a hassle that does happen as well when you multiply by negatives, and I'm not going to deny this one either. There is a time where if I want to multiply everything here by -1, let's say I put the -1 out here, and I'm a culprit of not having this problem, but I'm a culprit of writing this in this way, which causes the problem. People will remember to multiply this by -1 and this, well, I said -1, this by -1 and this by -1, and then on this side you say equals 22, and you almost forget to multiply by -1. So it almost becomes the same issue. What I try and do, I try and emphasize, and I didn't do this in my solution guide video, is just put times -1 on both sides, maybe even write the distribution and show that. Then you'll remember it's a -22. But that subtraction becomes a big issue. And you might be someone who's in denial and saying, no, I'm not going to mess up on that thing with subtraction. I'm going to do it right. Yeah, well, I almost don't believe... I can give some students the benefit of the doubt. If you practice it enough, you'll get it right, I guess. But it's easier for me to talk about the trying to find an additive inverse. That way, when we do those other problems, like if I want to get rid of this one, I do times -4, so that becomes a -4x, instead of just times 4. We're going to multiply anyway. We might as well practice the manipulation. Here's another case where people really do mess up, guys. And it's if you get some negatives here along the way. What if this was a -x? What if this was a -22? And now you have to subtract. And you're saying, all right, well, I'm going to put the big subtraction sign here, and 3y minus 3y is 0. And I'll tell you what, this is not just about this method here. I'm talking about when we do substitution or anything else. The negative still gets lost in the shuffle, or the minus. You say, I have a minus here, I have a negative here, so I'm going to subtract. And it just becomes a big hiccup and hassle and things where it's not correct what's happening suddenly. This may give the right answer here, I don't know, but that's a -5. No, see, this gives the wrong answer here. So when I subtract here, it's really, you're supposed to be subtracting a negative in that instance. I'm subtracting a negative. I'm not subtracting a positive. So everything here kind of changed, right? So you want to make sure that you're doing things the right way. So that should end up being a plus in the end. And minus negative doesn't look like plus to us, and it's just weird. I'm spending a lot of time on this because this is the last IM1 question, and it's really for me to discourage you from using subtraction here, whether or not you put it. It makes mistakes. Now, is there a difference? No, you should. If you do the math right, you should get the same answer. I know I probably wasn't answering your question when I stated what I was stating here, but I was trying to say here's why you shouldn't use subtraction, because a lot of times people don't get the right things out from it. All right, so that's going to be my answer to that one, guys, and that's the 15 minutes I spent on Integrated Math 1. I'm going to go down to Integrated Math 2, though, so thank you guys for asking that. Your test is Thursday or Friday for Integrated Math 1. Check the solution guide video for the practice exam if you need to see more stuff. All right, I think I have 8 questions here. Let's see. 1, 2, 3, 4, 5, 6, 7, 8. All right, 8 questions here. Let's go and take a look. Starting with the first question, which is long. How does solving a problem that is a perfect square relate to factoring a non-perfect square normally? For example, how would the equation 18x squared plus 14x cubed plus 32x squared, which as you solve becomes a perfect square, relate to the process of solving other equations that aren't perfect squares? I was kind of with you in the beginning, and then you gave me this problem, 18x squared minus, hang on, let me write this down. I like this plausible deniability of not seeing the questions beforehand, and then I go, maybe I should have seen the questions beforehand. I'm seeing 18x squared minus 48x cubed plus 32x squared. I would combine these two and get 50x squared minus 48x cubed. That's not a perfect, actually, I'd write in standard form, negative 40x cubed plus 50x squared. Even if I factor out the x squared, that's not a perfect square trinomial or quantity. If this is, maybe you meant to the fourth. Is that a perfect square? I don't know. It doesn't look like one right now. Is there a factor? Let's try this. And then, because I want to see if what you're asking is what I'm thinking about. There's a factor of 6. No, not 6. 8's not 32. Let me try 2 first. 2, if I factor 2x squared out, I get 9x squared. Well, that's a perfect square. Minus 24x plus 16. That's a perfect square. Oh, maybe this, wait. This works. Okay, is it okay? If this is what you're asking, 18x to the fourth, okay, there's that. All right, let's see the question. How does solving a problem that is a perfect square, like this one, you have to factor something, it's a perfect square trinomial, relate to factoring a non-perfect square normally? How does it relate? How would it relate to the process of other ones that aren't perfect squares? Well, okay, well, actually, the way I first thought you were asking the question is, how do you relate the process by which we factor non-perfect squares compared to that do we do perfect squares? Because what I ask you guys to do, and I don't know if this is your question, this is how I first thought. I thought you were asking, okay, say I factored this, and I can still factor this down, right? I thought you were asking, where are the discrepancies between trying to factor this like normally mentally, like trying to figure out, hey, what 2 numbers go here, blah, 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 versus recognizing that this is a perfect square trinomial and automatically knowing that this is 3x minus 4 quantity squared. Like I'm under the knowledge of that by seeing what's here. This is squaring 3x, this is squaring negative 4, this is doubling the product of 3x and 4, negative 4. So what's the difference between that and doing it? How does that change? So I don't know if that's what you're asking, but when you said solving, and I mean, one of the things is this in itself will only have one solution, whereas the other ones that factor would have 2 solutions. How would it relate? Well, you do say the process. That's why I saw that. You said the process of doing it that aren't perfect squares. Because you can take this thing down here, and you can try and factor this thing down to your, I should try 9x and 1x or 3x and 3x. Because these are positive product negative sum, I'll do minus and minus, and 16 can either be 4 and 4, or 8 and 2, or 2 and 8, or 16 and 1, or 1 and 16. You can tell there are 10 different combinations to try. 9x minus 1 times x minus 16, 9x minus 4 times x minus 4, 9x minus 8 times x minus 2, 9x minus 2 times x minus 8, 9x minus 16 times x minus 1, and all the ones with 3x. And if I did that in that order, all 5 of those wouldn't work. And then 3x minus 4 times 3x minus 4 would have worked. That would have been the 7th try, the 7th attempt. So that takes a while. How would the process relate to the process of solving? Okay, so let's say this. Let's say this then, based on your question. Why am I allowed to use this? Well, let me keep this up. Why am I allowed to do a process that brings me straight from here to here, which, by the way, that process is recognizing that that is 3. Well, I have to erase something here. Let me erase the top now that we're here. What's the relation of recognizing that this perfect square trinomial could be written as, recognizing this is 3x squared, this is double the product of 3x and 4, and this is 4 squared, so that it can then become this right here. So how does that process relate to the process we're doing right here? Well, I don't want to recommend describing the process when it comes to factoring, but when it comes to distributing, I think we can talk about that a little bit more. So I'm actually going to erase all this here. This goes back to when we were looking in Module 5. This was, I believe, Unit 2. So in Unit 2, let's look at 3x minus 4 quantity squared here. Well, yeah, let's do this one first. So that becomes 3x minus 4 times 3x minus 4. If I want to multiply this thing out, I can FOIL it, which means I do 3x times 3x, which is 9x squared. I do 3x times negative 4, which is negative 12x. Negative 4 times 3x, which is negative 12x. And then negative 4 times negative 4 is positive 16, which becomes 9x squared minus 24x plus 16. Okay. So that's what it distributes to, right? So which means if this distributes to this, that means this factors to this. Great. Or this factors to this. Now, a step that I'm going to write in between here is, see, you might notice that these two are the exact same thing. Sign, like terms, value, all of them are the exact same. So another way to write this is doubling it. Minus 2 times 12x plus 16. And you also might notice that that plus 16 was a result of doing negative 4 times negative 4. And this 9x squared was a result of doing 3x times 3x. So, you know, the reason why this thing kind of comes to be the way that it is, 3x squared, you might notice 3x times 3x is 3x squared, negative 4 times negative 4 is negative 4 squared. You know, that's kind of what happens here is when you FOIL this thing out, the process that occurs here is the firsts are equal. 3x times 3x are the same thing. Multiplying something by itself is squaring it. Multiplying something at the end by itself is squaring it. And the two middle terms are the exact same, so you can double them instead of adding them together. So there's a recognition involved with those things. I don't know if I'm answering the question, but there's a recognition involved with those things there that says that's why we can factor backwards in the same kind of way. If we understand this way, we can go that way with the same notion. Can you identify that this is a perfect square? Identify this is a perfect square, and then do that here. So this one has that lucky process of this is always 2 of the same number. That's why it's squared. It's 2 of the same number. This is always 2 of the same number in the back, and the middle will just always be literally 2 of the same number here, but added. Normal ones don't have that luxury of doing that, so we don't get a shortcut for normal ones in the same process, but these ones get that one. I don't know if I answered what you're asking there, but you know, we fortunately get that process, and if you recognize it, you can use it. And they both relate in the same way. They both have to do with foiling stuff, but this foiling is special because you're multiplying the same thing twice here. You're multiplying the same thing twice here. And when you multiply the outside and inside, they're the same things that add. That's very special in that way. Other normal factoring doesn't get that special opportunity to get that. Anyway, I keep saying the same thing over and over. I hope I answered it. I don't know if I did. Thank you for asking it. I'm sorry for spending a while on that one. All right, let's move on down to the next one. How do you know the difference between graphing absolute value functions and quadratic functions? Well, you know what the appearance looks like? Everything's based on behavior. You know, this talk can go massively deep if you wanted it to here. But let's break down the concept between two functions that have very identical looks to them here. If I graphed I'll say f of x. If I graphed f of x equals 3 times x minus 2, absolute value of x minus 2, minus 4 here, versus g of x equals 3 times x minus 2 quantity squared minus 4. You might be asking about how would I note the difference between these two? You know, what are the discrepancies of these two guys here? What changes in behavior? And I'll just say it's all about the behavior. Everything's all based on their parent function. This one is absolute value of x. This one is x squared. Everything is based on their parent function, really. And I'm going to go back to these as well. But the idea about these two right here, absolute value of x and x squared, is an absolute value of x graph will just go V-shape because the absolute value of numbers are just the positive version of their number. The absolute value of 0 is 0. The absolute value of 1 is 1. 2 is 2. 3 is 3. 4 is 4. Negative 1, absolute value is 1. Absolute value of negative 2 is 2. And 3, 3, 4, 4. And it goes in a linear fashion. There's linear growth. However much I go over on x, I go up the same amount on y, or at least a constant amount on y if I go a constant amount on x. So the same thing goes right here. It keeps the behavior going. What we have is a shift in vertex here. Negative 2, negative 4. It would go over 2, down 4. Remember, opposite, same. And then a stretch factor of 3 means that it would just go taller. It would go more like this instead. But it still maintains absolute value behavior as a V-shape. Because absolute value, it does make a sign positive, but it still experiences linear constant growth. So instead it just goes upward kind of like that. It's taller and it goes like that. A quadratic, in comparison, I'm going to hide this one away here. I'll make it kind of transparent. A quadratic one by comparison, if I do, let's make it blue. That's what I'm doing. By comparison, if I have a green one here, let's look at y equals x squared in the beginning. This is a parabola, and the U-shape idea is the behavior of parabolas have a quadratic growth. When I square 0, I get 0. 1 is 1. That's the same as absolute value. But 2 squared is 4. 3 squared is 9. 4 squared is 16. That's not a good quadratic. Let me do this again. There's a increase in growth in just it. There's no slope. It increases over time where I'm multiplying something by itself and it becomes much larger in that form. It's always curved in that U shape. All quadratics behave this way. So even when I have the 3 times x minus 2 squared minus 4, I have the same vertex as this other guy here, over 2 down 4, and then everything becomes 3 times taller, you know, like this, whatever, and it has a U shape. That's not really a U shape, but it has this kind of U shape thing to it. I'll pretend like that's my U shape, and it stretches a lot more there. I don't know if I'm answering the questions always right. It's kind of hard to do sometimes based on what you're asking. But with this one, guys, or to whoever's asking it, one has U-shaped behavior, one has V-shaped behavior based on how they grow. The nature of quadratics is it grows in that quadratic fashion. 1, 1, 2, 4, 3, 9, 4, 16. Whereas absolute value is just 1, 1, 2, 2, 3, 3, 4, 4. The stretch factor stuff is just affecting the way that it's already grown. Sorry, it takes the way that's already grown and it just manipulates that, but otherwise its growth behavior is like that. And that's why, you know, these ideas of this tableless graphing that I talk about with you guys is important for when we do something like, what if you get this one? 3 times the square root of x minus 2 minus 4. Now you just got to know what a square roots graph behavior looks like, which is like this, and then we do the shift, 2 over, 4 down, and then we stretch it 3 times larger. And what if you have, I mean, I'm not going to go very long on this, but what if you have, let's see, m of x, I don't know if that's the thing, equals 3 times x minus 2 cubed minus 4. And what if you have n of x equals 3 divided by x minus 2 minus 4? And then you do p of x equals, 3 log, I don't know, I'm not going to keep going. But the point is, all these have that same displacement thing and vertical stretch factor. The difference is, how does the behavior of a square root function go? How does the behavior of a rational function go right here? If you know those, everything else just does displacement and stretch factor stuff from these. So when you're asking about the absolute value in quadratic, you really just have to ask, what's the difference between this and this? And the difference is their growth pattern, and this and this. All their growth patterns are all just different. These just manipulate and transform that growth pattern. Okay, so anyway, V-shape for absolute value, U-shape for quadratic. Again, I don't know if I'm answering these well enough. I like to take the questions that you have and get an over-encompassing view of it, and hopefully that really helps. About a half hour in, let's go down. When you have a perfect square trinomial, how many answers will you have, and can that amount ever change? Well, the answer should be 1, unless you look at like the last problem I did. Let me go back to that. Oh, did I delete that part? Oh, I can go to the person's question. Okay, so I kind of deleted a part here, but let me go back to that other person's question when I have a perfect square trinomial. It depends if there's more in it. Let's see what they wrote. 18x squared, I don't want red. 18x to the fourth is probably what they meant to write, minus 48x cubed plus 32x squared. Let's say this all equaled 0. I can factor out a 2x squared, and within here I did have a perfect square trinomial. That was 9x squared minus 24x plus 16. Now, here's the thing. This is part of your product. If this times this equals 0, either 2x squared equals 0, so x squared equals 0, so x equals 0. See, this is one of your solutions here. This is not a part of the perfect square trinomial, but this is a part of the factorization where a perfect square trinomial existed. This thing's a perfect square trinomial, though. 9x squared minus 24x plus 16 equals 0. And if I solve it by factoring, I'm going to factor that down to that 3x minus 4 quantity squared. I did this in the first problem, the first question that was asked in IM2. I take the square root of both sides. I get 3x minus 4 equals square root of 0, which is 0. 3x equals 4, divide both sides by 3, I get x equals 4/3. There's only one answer. These things have what's called a multiplicity of 2. If I graphed this thing, I take it back because this is a quartic, but okay, I'm going to answer this in 2 different ways. This was not originally represented as a perfect square trinomial. When I factored, I got 1. The perfect square trinomial only had 1 solution, but there was another solution in the whole quadratic equation. So when you ask how do you, when you have a perfect square trinomial, how many answers will you have? Can that amount ever change? If your only factorization was from a perfect square trinomial, there's only one answer. There's only one answer, and it would just be that one. This has what's called a multiplicity of 2, which means if I graphed just this part, y equals this, I'd have a parabola that hits on the x-axis. The vertex, boom, hits on the x-axis. That's why there's only one solution. It bounces back up, which is kind of cool. There's something else to this one. If I graph this whole thing where it actually hits twice, I'm not going to get into that. But yeah, there's only one answer, and it's only because it would only hit once at that point right there. It's because the vertex hits. Most parabolas would hit, boom, most ones where we solve hit twice. That's why we see it, 2 solutions there. So yeah, only one solution. If the way that I'm answering is just part of this part, oh, actually I should say this part right here equals 0, there's only going to be one solution, only for perfect square trinomials. That's what's so nice about those bits. Now, we've solved by completing the square. Actually, no. There's not only one solution. Timeout. If you have a perfect square trinomial not set equal to 0, so if you're solving by completing the square, what if I have the same thing, 9x squared minus 24x plus 16, but what if it equaled 25? Now suddenly you do have more than one solution here. There's a perfect square trinomial on this side. I was assuming you meant set equal to 0, which was a bad assumption. I was going off the previous problem I had. But this one, when I factor it down to this, and then I take the square root of both sides here, now I get plus or minus 5. So now when I add 4, and I divide by 3, I'll get either x equals 4 plus 5 divided by 3, which is 9/3, which is 3, or x equals 4 minus 5 divided by 3, which is negative 1/3. So now I get 2 different answers there. So with a perfect square trinomial on one side, it factored down to present the possibility of isolating this to 1x, but I get a plus or minus on this side because there was another number there. So I could have 2, 1, or 0 solutions, all depending. I'd have no solutions if this was negative, taking the square root of a negative, there's no real solution, blah, blah, blah. So, I mean, it depends on what you're talking about. If a perfect square trinomial is set equal to 0, one solution. If it's set equal to a positive number, 2 solutions. If it's set equal to a negative number, no solutions. I mean, it depends on what you have there. If it's set equal to 0, you are going to have one solution. If that's what you were asking, then I'm happy to have answered it that way. Okay, here we go. How do you set up the problem when it's a word problem? Well, if we're talking about the stuff in the unit that we're in right now, I'll let you know, for the most part, they're kind of already set up for you, meaning they'll model it for you. The only real exception is if we have something where we have to say the area and then we're doing base times height, and that sets it up. So, you know, you've seen word problems already a little bit in the past, and they say something like they throw a balloon up in the air, and it's by the model, blah, blah, blah. The equation's kind of already written. Now, there's more to it that I can talk about here in a second. There are other problems where they might say, hey, the length and width of a garden or of a backyard or something is represented by this, and the area is this. Well, we multiply length by width. So there's not a lot of setup that's in the difficult realm. It's not really about algebra that you're setting up with. It's more about geometry. It's, do I know base times height and length times width in that concept. Now, one thing that I do want to point to for you, though, let's say we're doing a problem where it is talking about, you have a thing, I'm not going to get deep into this, but let's say you have the height of something is modeled by, and you'll get a lot of negative 16t squareds because that's like natural gravity. Let's say plus, I'm not going to like solve it, but plus 60t plus 10. Now, there are things to this that I can talk about if you had to create this for yourself, especially if you take calculus or something. This has to do with force of gravity in feet per second. So this has to do with gravity in feet per second. So you'll see a lot of negative 16t squareds just as a result of that. This has to do with the initial velocity. That's going to be like 60 feet per second. This is feet per squared second. In feet per second. And then this has to do with the initial height in feet. So if you ever had to construct, we don't have to do that, but if you ever had to construct a word problem here, you could say, hey, starting at 10 feet in the air, they launch something 60 feet per second, blah, 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 straight upward. And then you're on Earth and gravity. So that would be it. Now, they might ask a question like this. At what point would the object be 40 feet in the air? So as a part of this model here, what you would do, h is the height represented for time. You would substitute 40 for h of t, not for t. You're trying to solve for you. For h of t, you would say, at what time will it be 40 feet in the air? You set it up like that. And then you solve for t. Now, I'm not going to actually solve this thing. I don't know if it's actually even a good answer or anything. But you set h of t equal to 40. At what time? And there might be more than one time, because I want you to think about it. If you're 10 feet off the ground for whatever, and you throw a ball straight up in the air, it might hit 40 feet going up, and then it comes back down and might hit 40 feet again. I mean, if it hits 40 feet once and it's not the top, it's going to hit 40 feet again. So we'll probably get two answers to that thing. So the setup is setting that equal to 0 in that kind of way. At what point will it be 40 feet in the air? They might ask questions that are not trickier, but they don't actually give you the number, and they assume that you got to know the number. At what point will it be back at your height? Well, if it launched 10 feet in the air, this is a 10 again. At what time will it be at the same height when you first threw it? Okay, this is 10 and 10. That might be another question like that. Or a question might be, at what time will it hit the water? If the water's at 0 feet or something like that. If you're on a dock that's 10 feet above water, they might say 10 feet above sea level. At what point will it hit the water? You want to see when it equals 0. So the equation's already set up for you. But now you got to substitute something for height to kind of answer that t question afterward. I hope that kind of makes sense there. And you solve it, quadratic formula, factoring, whatever it is that you do there. And then, like I said, you might have some other questions where you're trying to find the area of something, and it's modeled by them giving you like the length and width. The length is 2x plus 1, and the width is 4x minus 20, and then the area, is 50. So you got to say, okay, if this is a rectangle, I multiply length by width, and I get area, right? That's a setup. That's how I set it up. So there's nothing I have to create out of thin air. It's kind of provided for me, and it's logic of knowing the other things with it regarding height or area or something like that. That's the extent to what we're doing right there. But you could create, if you saw me create that one word problem, there's acceleration, force of acceleration in feet per second, which is negative 16 t squared. And then the initial velocity is that second number, and the third number is the initial height. You don't have to do that, but that is a part of what you may do at some point. All right, can you please go over how to simplify square roots again? Gladly. I don't know how deep I'll get into it, but the concept comes from several properties here. Well, it comes from one main property. The main property is, if we take the square root of a product, we can separate it into the product of two square roots. And the objective of simplifying, oh, by the way, check in the description section, I'll try and remember to do this, but check the link near your question to find what I did on Zoom that day. I don't know if I can do that because this is a public thing. I think I can still do it, but check the link where I do simplifying some radicals there as well. It's going to be the same stuff I'm talking about here, but I'm going to make up my own problems here. The objective of simplifying a radical is to factor out any perfect square factors that exist inside that radical. So what you should try and do, here's a list of perfect square factors I should be able to divide by. I'm not doing 1 squared because dividing by 1 doesn't change my number. But 4, 9, 16, 25, 36, 49. This is 2 squared, 3 squared, 4 squared, 5 squared, 6 squared, 7 squared, 8 squared, 9 squared, 10 squared, 11 squared, 12 squared, and I'm going to stop right there. You can keep going, but the concept is, look, if I have square root of 36, that's just 6. I'm not going to try and do anything fancy. That is a perfect square already. But let's say there's a number like the square root of 108, which is not a perfect square. It's not on this list, but it has a perfect square factor that exists inside of it, and maybe more than one. I recommend that you attempt to find the largest perfect square factor possible, because then you only have to kind of do one step on this thing. If you find a smaller perfect square that still works, and there are several that work here, then it might take a little bit more time. For example, I can divide 108 by 4. If I divide 108 by 4, I get 27. Now, this is a step I don't ordinarily write, and I won't write it after this time that I do it. But 108 is 4 times 27, so the square root of 108 is the square root of 4 times the square root of 27. If I use this property here and say I can split this up into their own square roots, this benefits me because I can take the square root of 4. That's why I chose this number, because I can take the square root of it. And that becomes 2 times the square root of 27, or as we just say out loud, 2 root 27. Now, if you use a calculator, you'll find out that the square root of 108 and 2 times the square root of 27 are the exact same number. It's around 10 point something, probably around 10 and a half. I don't actually know. It's probably around 10 and a half. Now, I'm not done simplifying this radical, because if the whole goal was to find a perfect square factor that comes out of this, 27 actually happens to have a perfect square factor in and of itself, and that number is 9. So I can split that up, 27, into 9 times 3. And like I said, I was only going to do this once. I'm not going to do that anymore. So that's root 9 times root 3. 27 is 9 times 3. Root 27 is root 9 times root 3. The square root of 9 is 3, so I can multiply the 2 by the 3, and I get 6. Now, this all kind of took a little bit of a long time to get down to 6 root 3, because I found a perfect square factor that was a little smaller than the largest one possible. And I'll tell you what, you can also divide this number by 9, but if I divide 108 by 9, I get 9 and 12. 12 has a perfect square factor of 4 inside of it, so that would take more than one step again. Why don't I keep going until my second number in my division does not get a perfect square factor? So how about this number? 36. When I divide 108 by 36, I get 3. 36 times 3 is 108. 3 is not only doesn't have any perfect square factors, 3 is a prime number. So already I know that 36 is the largest perfect square factor that could have divided out of 108. I chose 36. I can take the square root of it and get 6. I get 6 root 3, and I am done. I guess it took 2 steps to write this part as well, but I don't have to do any more breakdown. I just take the square root and I'm done. So my end goal for all these is to find the largest perfect square factor possible in my number. So it only kind of takes one step after that to do. Just take the square root of it. This takes a little bit longer, but the process still remains in what I'm doing here. So that's one way of simplifying radicals that we're really talking about, specifically square roots. There's another thing in rationalizing the denominator I won't get into, because I think we're not really doing that together. It's an important talk, and I think I could link you to some other videos at some point if you want them. Just ask me about it. Let's do another one, though. Let's do one square root of 192. Square root of 192 right here. Try and find large perfect square factors that go into this thing. I hope it's not 36 again. I hope that's not the largest one when I did this. I actually just came up with a larger one. So you could try. I could try and do things with this. If I divide it by 4, so here's how you should check. Let's divide it by 4. If I divide it by 4, I get 48. I'm going to not keep going for a moment, only if you think that this would take too long to do. 48 can also divide by 4. Heck, I could divide by 16. Those are perfect square factors. So I could get something larger. So I'm gonna leave it. It's not that this is wrong. It's just I'd have to keep going. So it's going to take a while. Can I divide it by 9? 180. No, I cannot divide it by 9. Can I divide it by 16? 160, 176, 180. Yeah, I can divide it by 16. If I divide it by 16, I get 12. But 12 can also divide by 4. That means I'd have to keep breaking that down. Again, if you're on that stage, maybe you do that. But if I found the perfect score in my head a little faster, so it might take a little longer. 4 and 16 works, 9 did not work. 25 will not work, it just won't. 36, I don't know. I didn't really check it. I don't think so because 180 goes into it in 36. 36 goes in 180. And then 182 skips. So not 36. I don't think 49. That would be a stretch. I don't think so. 49, 98, 196. No, not quite. Not 49. But 64 does work. And 64, when I divide it by 64 here, I think I also get 3 here as well. Now the square root of 64 is 8, so I get 8 root 3. And that's just done in one step when I found the largest perfect square factor, because this didn't have any perfect square factors left in it. 12 did, which I could break that down still. That'd be 4 times root 4 root 3. Root 4 is 2. 4 times 2 is 8. So, I mean, I skipped some steps along the way because I know what I'm doing in my head with that. That takes a while. Square root of 4 is 2. If you knew that 48 was 16 times 3, you could do that. Square root of 16 is 4. 4 times 2 is 8. You have 8 root 3. So again, you can get it that way as well, but if you find the largest perfect square factor pretty quickly, it can get you there as well. And anyway, that's the end goal. That's all I'm going to talk about right here. That's going over that concept. There are a lot of problems where I still do it, so just take a look at those. You find perfect square factors, you factor them out. Remember, if your number's already a perfect square, you can go about it that way as well. I can link you to an old video, and it's probably going to answer things the same way, where you do this, but there's another old video where you do that other one, where you can break it down to its prime factorization, and then from there you merge things together. I'd recommend you do this though. So I don't know, request those videos from me personally if you want. I'm not going to go out of my way to give them to you because I believe this was probably the best way to go about that problem. All right, here we go. How do you solve equations by completing the square? Now, you're not just asking how to complete the square here. So you're asking for the deep, deep talk on this. I'm going to kind of keep it light. So let's talk about how you complete the square. So completing the square itself involves creating a perfect square trinomial from something that wasn't before. So here's what I'm going to recommend for now. I'm not going to get into the deep advanced version. Only complete the square if you have a 1x squared and a even x term, meaning the linear term. If those things are good, if you have a 1x squared and even linear x term, then you would divide your linear coefficient by 2, then square that value. That completes the square. So the main idea is if I have x squared plus 4x plus blank, I take 4 and I divide it by 2 and I get 2 and I square that number and I get 4. That gives me a perfect square trinomial. The reason we complete the square is so that we can factor it down into something like this. So then, and I'll show you what happens next after that. But the reason to create this is so we can make this something squared. Perfect square trinomial. And I like earlier when people were actually using the phrase perfect square trinomial. I like when you guys use academic language like that. It's kind of cool. So let me just do one more here. X squared minus, let's use even numbers only, 10x plus blank. Divide negative 10 by 2, that's negative 5. Square that, I still get a positive 25. And that becomes x minus 5 quantity squared. So that's how you complete the square. You divide it by 2 and square it. And I used a whole IXL assignment for you guys to do, a whole activity for you to try and complete that square over and over and factor it down. Because what are we supposed to do with this? So what's the process? So I recommend you do this in problems, and I'll use those two examples again. I recommend you do this in problems where you have the 1x squared and an even linear coefficient. So let's say you wanted to, because you're asking about solving. Let's say you wanted to solve x squared, what was my first number? 4. X squared plus 4x plus 2 equals 0. So the 2 is not the number that makes the perfect square trinomial. So I move it off to the side. I move it off to the side right here. and I'm going to complete that square with the number. We remember what it was, right? It was a 4. I complete the square by putting in a 4 right there, and it gives me this perfect square trinomial. On the right side, I also have to add 4 because it's just a balance thing. Just like I subtracted 2 to both sides, I also add 4 to both sides. But my goal of doing this was to now factor this thing down. Now I get to write x plus 2 quantity squared. Negative 2 plus 4 is 2. The cool thing about this is I don't need this side to equal 0, like in factoring, zero product property, because I have a perfect square trinomial. Something squared is 2. Something times itself gives me 2. Obviously, that number is the square root of 2. But I take the square root of both sides to kind of get that part broken down here. And remember the plus or minus portion. And I subtract this 2 from both sides. And I get a negative 2 on that side because I subtracted, and plus or minus root 2. So if you recall, and I'm just speaking really specifically to my classes here, section 9.1 is where this part came into play. I have a perfect square quantity factored, and I take the square root of both sides. My intent of completing the square is to create something factorable squared so I can take the square root of it. So that's how you solve. You attempt to take the square root of both sides. And I do that by making a perfect square trinomial that I can factor down. The rest, I'll say, is 9.1. This is stuff I won't kind of hit hard on because you didn't ask how do you solve using square roots. You said how do you solve by completing the square. It gets into solving using square roots. And that's what I'm attempting to do. Let me do it for one other problem right here, kind of the other one we were talking about, that minus 10x. Let's look at x squared minus 10x equals negative 5. Negative 5 right here. So I already have a negative 5 on that side. So this on this stage here, I'm going to, whoopsie, hold on, x squared minus 10x. I'm going to add something on this side, and on this side I'm going to add something. This is that 25. Negative 10 divided by 2 is negative 5. Square that, I get 25. So over here I get 25 as well. This factors down to x minus 5 quantity squared. Negative 5 plus 25 is 20. And I do, once again, the rest is 9.1. I take the square root of both sides. The square root of 20, that's root 4. This kind of helps the person before. Root 4 times root 5 is 2 root 5. Here I have x minus 5, but remember I got to put the plus or minus here. If someone asks a question about that, I'll answer it. If I add 5 to both sides, I get x equals 5 plus or minus 2 root 5, like that. So that's the factorization. That's the square root. That's a simplification of the radical when I get that. Anyway, the process is pretty straightforward. If you have a 1x squared and an even linear coefficient, it's recommended. If this isn't a 1, I can't complete the square because I don't really have a square. The book does something on it when it comes to completing the square, as long as the number is a 4 or a 9 or a 16. But you have to make it into 1 if not. I say make it into 1 if it's not a 1, but I also say solve using quadratic formula otherwise, or solve by factoring if it's factorable. Neither of these two were factorable, and I think this is faster than quadratic formula if you just complete the square there. But this has to be a 1, and this should be even. Otherwise, you're going to divide by 2, you'll get a fraction, and I don't think we like to do fractions there. All right, so I hope that answers the question there. Thank you for asking. I'm at 52 minutes here. The power hour looks like it's going to be an hour. All right. Oh, one more question here. What does the equation look like if the discriminant has no real roots? Wait, what is the equation or the discriminant? Oh, what does the equation look like if the discriminant has no real roots? So the way the person's asking it here, it sounds like they are under the understanding that the discriminant would be negative if you have no real roots. By the way, some people here might not know what the word roots means. I don't think we've used that very much in my class. Roots are solutions. Solutions to the equation, x-intercepts, things where they cross the x-axis, things like that. So roots, we're talking about solutions. Kind of same thing, no real solutions. So let's first write one that doesn't have them. I'm going to do an obvious one here for myself. I know it's obvious. X squared plus 10x. Oh, whoops, I did it wrong. X squared plus 2x plus 10 equals 0. And let's solve that thing. If I apply the discriminant, guys, is b squared minus 4ac. This is a part of the quadratic formula. This is inside the square root. The whole thing, looks like that. The discriminant is just the b squared minus 4ac portion. The important thing about it is because we take the square root of it, the square root of a negative doesn't apply, right? There are complex roots. Those are the things we're talking about, but there are no real solutions to that. So if we have b squared minus 4ac, and if it's less than 0, then there are no real solutions, or as the individual who wrote this said, no real roots. So let's do this one. B squared, just the discriminant. b squared minus 4ac would give me 4 minus 40, which is negative 36. Aha! A negative discriminant means I'll have no real solutions. Now, someone asked what the equation looks like. How did I know that this one would give me it? I mean, I'm going to try and do something b squared minus 4. I'm going to do something with you in a bit to try this. But I'm trying to think of the best way to answer it. But, you know, the b has to be small enough for the a and c combined to be large enough so that it becomes negative when you subtract. I don't know if that makes sense when I say that. But, you know, here, okay, so here, check this out. We're trying to see what is the equation looks like, what the a, b, and c look like when you have ax squared, let me get rid of, I wish I planned these. You have ax squared plus bx plus c equals 0. We're trying to figure out what the equation, what the a, b, and c look like when you have a discriminant with no real roots, when b squared minus 4ac is less than 0. Well, if I added 4ac to both sides, you'd say, well, your b squared has to be less than 4ac. That makes sense, right? The thing that I square has to be smaller than the thing I'm going to subtract. That's what gives me a negative. Now, I don't know if this will be a little much for you guys. If I take the square root of both sides, I'm going to write the absolute value portion here. The absolute value of b has to be less than the square root of 4ac, or 2 root ac. Boy, that's going to be quite a hassle for you to look at there. Now remember, for discriminant, it doesn't matter if b is positive or negative, because when I square it, it'll become positive. That's why I have the absolute value part. b could be negative 2 or positive 2. It's still going to give me that same discriminant. A or c being negative does matter. And look, honestly, we don't get a lot of a's that are c's and negative. And honestly, we don't get a lot of a's that aren't even 1. So it's almost really about the c value. But the product of a and c, boy, you know, this does not really help to look at it as a square root. This doesn't help me see what this is. But 2 times the square root of this thing has to be greater than the absolute value of b for this to work. You know, I don't like looking at it like that. Let's keep this one here. But that did kind of help me say something. All right, b squared has to be less than 4ac. That's the best thing I could do for you. Let's do this. Let's assume that a is 1, because a is 1 a lot, right? A is 1 a lot. So now if a is 1, 4 times 1 is 4. So b has to be less than 4 times c, b squared. Does that one help a little bit more? Now, whatever I square, if this is a 1, my b squared has to be less than whatever 4 times this number is. So when I had x squared plus 2x plus 10 equals 0, so b squared is 4. Is 4 less than 4 times that? Yes, it is. If 4 is less than 4 times 10, then I'm going to have a negative discriminant. This is assuming this is 1. How low or how high can some of these numbers get where then the discriminant changes? What if I have a 6x and an 8? Now I have b squared is 36 and 4 times 8 is 32. Is this less than 32? No, it's not. So this will work. Okay, but if this was a 10 again, then this would be 40 again, and then suddenly this wouldn't work again. And remember, even if this is a negative, it's still the same thing. I squared, I get a positive 36. So that still wouldn't work. That would still give you a negative discriminant there. So that's assuming this is a 1. Suddenly when it changes, now you got to do the product of those things. It's all about b squared minus 4ac. What does it look like? It looks like something where your b squared is less than 4ac. That's really the only thing I can say when it comes to discriminant. Anyway, I wanted to experiment with that as much as you asked me it. Really what I was getting to... here's something that does actually help for you. So the point I was getting at was sometimes if this number... Because this is what I said before, like this. If this number... Like this number's got to get kind of large. If this is a 1, this number's got to kind of get large to offset me squaring this number. Right? So once I see this number gets a little large, that can make sense. Now, if it's the other way... If this is what I was accidentally going to write to start. If this was the other way, will clearly work. I got to square this number and do 4 times that. This is clearly going to be not factorable. This is clearly going to have solutions. So these ones look like they'll have solutions to them. Here's another kind that does have solutions. Here's what I wanted to point out. Let's assume this is, I don't know if this is 1, but let's assume A is positive. I like looking at positive A values. Who cares if B is negative? Remember that? Doesn't matter if B is negative. But if C is negative, once you hit a negative on C, assuming A is positive, once you hit a negative on C, all of these will have solutions. Because what happens when you do B squared minus 4AC here? I do B squared minus 4AC. I get a negative 10, and a negative times a negative is a positive. You automatically add here. You add. Once that C is negative, you're adding. That's another reason why I like making my A positive, even if it wasn't to begin with. If I bring everything over to the other side, if I multiply everything by -1, that's when I like making A positive, because then I know it doesn't matter if B is positive or not. B could be negative, and I still get a positive 4. Once C is negative, then you're getting a discriminant with a positive discriminant. And really the reason is because you're hitting, this means a negative y-intercept. And so an upward facing parabola with a negative y-intercept means it's got to hit the x-axis twice. But with a positive y-intercept, we don't know if it's going to go down low enough to actually hit it. So another question you might be asking, what does the equation look like? It also means a graph that doesn't have x-intercepts. It also means, if this is plus 10 again, this also means a graph that doesn't have x-intercepts. This graph somewhere, it crosses at 0, 10, and it doesn't ever hit the x-axis again. But if it hits 0, -10, then yeah, it hits the x-axis twice, like that. Anyway, I hope that answered that for you there. I'm at the hour mark. This was my power hour. Thanks for watching, guys. I hope that was all fun for you. Remember, check the questions down below in the description section, and I am done. Take care.